So in the previous segment we were talking about the three different types of fields primarily. One is the displacement field, the pressure field and the velocity field. And we also discussed a bit about the intensity or the sound energy basically, which is very important parameter in the field of sound. So let's in this segment what we will do is we will try to derive the expression for the sound energy and the intensity of sound, okay, because that's what we perceive. Like light intensity, we perceive sound intensity. Okay. Now for that, let's say suppose we have the pressure versus the volume through which the sound wave is propagating, and we said that because the compressions and the rarefactions are happening so quickly and the thermal conductivity of air is not that great, and that's where the heat transfer is almost zero. So it's an adiabatic process, and so the PV is like some curve, PV raised to gamma. Now under that, if that's the process through which the gas is going through, we can think of say a small volume element, say dx dy dz, okay, of volume element. We are inside that tube, so which was initially at say V naught, and then the corresponding pressure was say P naught, the equilibrium pressure, and then as soon as the wave passed, it had a volume V and a pressure of P naught plus P, right. Now in doing that, and then we are trying to evaluate how much energy is contained in that, means how much energy we used to do or the wave to be propagated. Now there will be obviously two parts. One is the kinetic energy. So the kinetic energy portion will be what? So half times mass will be say rho naught times this dx dy dz. So this is the mass, and the velocity square will be say this, right. So this is the kinetic energy. And what about the potential energy? Potential energy will be the area under this curve in a way, right, the PdV integral sort of. So and how you can find this out, almost like it's a, you can consider for this small change of volume, you can think that it's a straight line, so it's a trapezium. So almost like 2 P naught plus P over 2 times V naught minus V, right. So that's the work done. This is the area. Area of a trapezium. Okay. Now, so this is almost like I'll say P naught plus half P times V naught minus V, right. So now this is the work done which is being done instantaneously at any, so all those things are time dependent. But because we are now considering the harmonic oscillations or the harmonic plane wave propagation, we should think in terms of average energy over a period. Okay, so that will give us a proper idea about how exactly how much total energy is getting or contained in a volume of air. because if it's complete sinusoid, there is no in half cycle it is getting into and half cycle it is coming out of that thing. Now if we do that, so that means we are trying to take the average over a complete cycle, and in doing so this will just won't what do I call contribute to anything, right, because this is just a constant. Okay, so what we actually are looking for is this half P V naught minus V is the actual work which is being done by the or when the wave is propagating through that volume. Now remember from the earlier expressions which we had, this P was what we said, negative of rho naught c square d xi over dx, right? And what about this V naught minus V? It is a change in volume. Okay, so will that not be equal to say d xi over dx times dx dy dz? Because see, this is the original volume and its new volume will be how much? Say 1 minus delta times dx dy dz, right, which is nothing but, if I want to write 1 plus d xi by dx dx dy dz. Okay. Now, so this is the new volume, this is the original volume V naught, this is V. So V naught minus V is that negative of d xi by dx into this, right? So negative. Fine. So you can think like that also, right? Say, how do I go? Say suppose rho V is constant. So how do I go? Say rho dV plus V d rho is 0. So d rho by rho is negative of dV by V, sorry, V, and so this is where you can do that, and that is this, so you can, okay. So this is the thing. Now if you multiply, what will you get? So this will become half rho naught c square d xi over dx squared times dx dy dz, right? So that means I'll write, where did I write this? Okay. So your total energy density in a way means in a, not density, I'll say in a small volume of dx dy dz is half rho naught d xi over dt squared plus what we had here, half rho naught c square half rho naught c squared d xi over dt whole square times dx dy dz, right? So in fact, yeah, so and if you really want to get the complete energy in a volume, you can integrate this over dx dy dz. So, you will actually get the total energy which is contained in a given volume, and in fact this part is the energy density. It's like joules per meter cube sort of. That is why when you are multiplying with meter cube, you are getting joules, and then you are integrating over the whole volume, and this is time averaged. So that's very important. Means we are actually seeing time average thing always. Okay, we will take the average of this thing. So that is why we could in fact remove that P naught term. Yeah. This can be written in a better way, like say integral of half rho naught u square plus what happened? Now this is if you see that the expression which we had is here I am writing it. P is nothing but rho naught c square. No, not this. Sorry. Your rho naught c u, right? If you remember this long back, I think we did. Oh, here. Sorry. Right? So if you put that, so your P is u rho c. So then, so this is something is missing. I think it is wrong, right? This should be dz by dx, right? Yeah. So this is wrong. So sorry. Okay. Yeah. So that's what I was thinking. So dz by dx. So then P that you can use now. Yeah, rho naught c square dz by dx, right? So its square is p square over so p square over rho naught c square times half rho naught c square. Oh, something, this is c fourth, right? It's square. It's square, right? Z dz by d square, so rho naught square c fourth, right? Yeah. Dx dy dz. So that means this is equal to integral of half rho naught u square plus half rho naught c square p square. Is that fine?
Yes.
So this the time averaged thing is your energy which is of importance. Okay. Again, this is your energy density, and it is an instantaneous one. means every time it will change. That is why we are averaging it to get the total average total energy. Okay. And here you see this information or relationship between P and U is valid only for a progressive wave. So please note that there are some things which are valid always, some things which are valid only for given conditions. Now this you can actually replace here and write everything in terms of U also. Okay. So either you can replace P to write everything in terms of U, or you can replace U to write everything in terms of P by using this. Fine. Okay, so that's the energy. And if you want to calculate intensity, basically what you have to do is let's try to do that for the sinusoidal or harmonic wave which we have been dealing with. Okay. Now for that, so the total energy density, how to calculate? So half rho naught U plus square, we are now splitting. So the wave energy which is going in one direction. So I am just, so this is TE plus, because TE plus and TE minus will be completely depending on that wave which is going in that direction. So this plus what was there here, this P square over 2 rho naught C square. So P plus square by 2 rho naught C square. But P plus now is can be written as yeah. So this is equal to half rho naught U plus square plus half rho naught C square, but here you can write rho square C square U plus square, right? Then what is getting something, okay, so so this will become half rho naught U plus square plus half rho naught U plus square, right, because C square gets cancelled. Then you get rho naught U plus square is the total energy if you write in terms of only U, velocity. Now in fact, as I was mentioning in the previous class, to calculate energy you should always convert them into the real part and then multiply, because this is a square term, you see. You can't just do with complex number and then if you expect that by taking the real part you will get the real part of energy, it won't work. So if you just substitute, the U sort of thing, U plus, let's an example, say omega A plus of sine omega t minus kx type of thing. This is a general velocity profile, okay, when A plus is given as zeta. Now if you substitute this and integrate over a total time period, okay, if you substitute it here and integrate over a time period, so you will get the total energy plus for such a particle field to be equal to rho naught U plus square over 2, okay. So this is normal, means you just integrate it and it is square, because you know that square of any sinusoidal functions If you integrate, you will get half generally. So this half is coming from that, and this u plus is coming from the fact that omega a plus is nothing but u plus. Okay. So that's how you will get it. And yeah, and then if that you want to write in terms of p plus, because now u plus and p plus are related, so you can write this as p plus squared by 2 rho naught c squared. Right. So this is the average energy content of the forward moving wave. Okay. Now when I am saying average, it is averaged over time, and this is averaged over a full cycle. Okay. So I'll put this averaged. Now if you try to calculate the intensity now, you just imagine that this kind of a wave is in 1 second, how much of the tube length will be passed in 1 second? C, right? Because c is the speed. In 1 second, c length of the tube's wave would have passed by a particular point. Are you getting? Because see, this is what try to imagine now. This is suppose you are standing somewhere here. Suppose here you are standing, and that is the energy which is, if you calculate what is the total energy at that location, at that which is passing through. So this is that, isn't it? And time averaged. But then if you wait for say 1 second, what is the length of the wave which will pass through? C, because it's the wave speed is c. So that means, and this is the joules per meter cube sort of, isn't it? It's the density of the energy, and you are sitting there and we are seeing a column of c length passing through us. So if you multiply by c, then you will get the watts per meter square which is passing through you, right? Right. So that means this times c, which is nothing but p plus squared over 2 rho naught c, is the intensity of the energy. That means it is this much watts per meter square is passing through you. Okay. And this is the energy which for a plane wave when we are hearing, so we feel this intensity. Okay. And then because we feel this, a level has been chosen based on this. Okay. Now a reference value of, as I was telling, 10 raised to minus 12 watt. So I naught, the 10 raised to minus 12 watts of intensity per meter square has been chosen to be the reference value, and with respect to this all the levels are defined, and that too in log scale. That means sound intensity level is the thing which is defined to means what, quantify intensity, and that will be 10 log to base 10. Okay, what's happening? Of any intensity divided by I naught. Okay. So this in dB. Now, what this tells you, means physically, what this equation means is this: if you are given to an ambient where no other sound is there, some sound is played, and you are asked to feel the sound. You felt it. You gave some number to that loudness. Okay, this is very qualitative. You gave some number to the loudness. So you gave, say, X. Then the other person who was actually controlling this sound, he increased it, and he asked you to tell him to stop when you feel when the sound is 2x. Okay, so you were closing your eyes and you were feeling the sound. You felt, okay, now the sound is twice loud. Then he will stop it. So now your sound is 2x loud. Then again he increased, and you again stopped when the sound is double the loud here. If you do that, say 4x loud, and now you go back and see how much intensity that person had given, because he can control the intensity by electrically changing it, and he can measure even the intensity very easily because he knows how much power he is giving. Now if you see the intensities, they will not be in this order. In fact, see, sorry, there is a slide. Now, you were not asked to do this. Sorry, I was having this in mind for intensity, so I just told like this. In fact, you were told to stop him as soon as you have a same amount of increment in loudness. So x to 2x, 2x to 3x, not this 4x, means 3x, then 4x, means you are just feeling that sound same amount has increased. But then when you see the intensity, it will not be in this linear order. The difference would come as a multiplication type. The intensity would have increased, say 1, 2, 4, 8 like that, or 1, 10, 100, 1000 like that, depending on this difference. Are you getting this? The difference was constant, which you perceived. Okay, you felt that, okay, the loudness has increased the same amount now here, the loudness has increased the same amount here now, x, the same amount here now. But to increase the loudness the same amount, what you perceive, the intensity would have increased in order of magnitude type, means in logarithmic scale, 1 to 2 to 4 to 8 sort of thing. And that is why they have defined a log scale so that it will be a linear. That means, and then what this 10 here sitting is, every means suppose the intensity, the first intensity is I, the second intensity is say 10 raised to 1 over 10I, the third intensity is say 10 over 2 over 10I. Now these intensity increments will give you equal increment of loudness, the perception of equal intensity of loudness, and this specific increment is called 1 decibel. Okay, so that is how once you go to say 10 raised to 10 by 10I, you get 10 dB increment. So that is the meaning.